Today we're going to talk about VSEPR, and it appears that some of you received a chart like this in the past. I cannot remember if I gave Mr. Belcher one of these charts or not. Does anybody remember seeing, unless you had me, does anybody remember seeing a chart like this, or were you given a chart like this? Did it look like this? Okay, great. And I'll actually show you what all of these look like and how some of these names are actually derived. But one thing that I do want to point out, and if you have a highlighter, because this is, again, my vocabulary, my way that I remember it, and if you have your way from General Chem and you still remember it, that's cool, that's great. Okay, I'm just throwing out other ways to help you remember this. The line up here at the top, if you have a highlighter, highlight where it says the number of potential atoms surrounding da-da-da-da-da-da. Okay, if you have a highlighter, highlight that, because that has a lot of significance with this very first row with the 2, 3, 4, 5, and 6. Okay. And I will take this chart away once we start doing the examples, but you'll still have it in front of you. Obviously, you'll have to memorize this for the tests, quizzes, AP exam, all that stuff, just like what we did last year. But let me define a few things here. In AP Chem, all we care about is the molecular structure. I think in General Chem or Honors Chem, I had you guys tell me two names. The first name was what the shape was with the lone pairs of electrons, and then the second shape was what the name is that the atoms alone form. That's all AP cares about, the name that the atoms alone form. So I'll try very hard not to ask for the first name. And the first name was always one of these 5. And these are the 5 basic structures for what we care about. Okay? And if you do organic chem, then you're only going to worry about tetrahedral, trigonal planar, and linear. So you only have to worry about 3 when you get into organic. So over here, these are some unusual characters in the mix here. All right, so the top line that I had you highlight says the number of potential atoms surrounding the central atom is defined as the number of external atoms, so however many external atoms we have, plus the number of lone pairs of electrons. And that'll have a little more significance when we actually start drawing this. So keep that in mind. And do realize that we'll have values of 2, 3, 4, 5, and 6 as our potential. So when I go over this, refer to the sheet and look down, because I've already got it memorized. I don't expect you to have it memorized at this point. So that's what I'm talking about. Then the column here on the right, it talks about the name of the molecular compound or the molecular geometry with no lone pairs. So the structure has atoms wherever there's a spot for an external atom. There's no lone pairs. So that's what this deals with. So no lone pairs, 1 lone pair, 2 lone pair, 3 lone pairs. And 3 lone pairs is the maximum that we're going to deal with. Now I know that there are other scenarios where you could have 4 lone pairs, but that's not what AP cares about, okay? And then down below, I have the rules, and you can't see all of it here on the video, but on the sheet you can see, I think I've added 2 more spots there. Okay, so, actually I'm going to turn this off. Actually, let me go to the shapes here, which is on the flip side. Okay. So looking on the other side of the sheet, this is also available for you. Does anybody remember what the name of this shape is? Tetrahedral. This down here is a linear. This here is a octahedral. Very good. I don't know if I can scoot. I can scoot it over. All right. What's this guy? Trigonal bipyramidal. And then the one on the bottom here, trigonal planar. Okay, great. Okay, well, let's turn this off. Let's go through the shapes real quickly here. The first one that was on the sheet, I should have wore black, daggone it, is a linear shape. Okay. Now the reason why it has the name the linear is because it actually, all the atoms form a line. Okay. So when you look at the shape, there should be how many external atoms? 2, okay? And sometimes you might have a diatomic molecule like nitrogen, oxygen, hydrogen, whatever. And what shape does that form? linear as well. 2 points make a line. So even though that is not on our sheet, you may see sometimes that you have a compound or a molecule that just has 2 atoms total, like nitrogen. That's a linear shape, okay? So linear, typically the ones that we're talking about when we're looking at the shape actually has a potential of 2. Again, what does potential mean? The number of external atoms plus the number of lone pairs. So when you look in that first column, you only have how many options? 1. It's linear. Okay? Trigonal planar actually looks like a triangle that lies on a plane. Okay, so trigonal planar, and this would be a good example of like sulfur trioxide. So trigonal planar actually means that you have a triangle, and the angles here are what? 120, and if you forget, just say, okay, I got 360, divide that by 3. You can do that math real quickly. And on the AP exam, they'll ask you about angles. The good news is there's only 4. 109, 90, 180, and 120. Okay, so those are the ones that you have to remember. So trigonal planar looks like this. What's my potential for this? 3. If I had, say, sulfur dioxide, okay, recall that this lone pair of electrons does have an influence. It won't allow these guys to be 180 degrees away. It does repel the other 2 atoms. So we still have that trigonal planar shape, or trigonal planar, however you want to pronounce it. So if we look at this lone pair, what shape does this form? You got 1 lone pair. Look at your table. So before I do that, what is my potential? 3. So you're going to work in the column that has 3, and then there's 1 lone pair, so you go 3 and then the 1, boom, bent. Isn't that cool? Okay. Tetrahedral we've already looked at numerous times. Okay. So the tetrahedral has the potential of what? 4. So if I look at this, this might represent ammonia. So I have 1 lone pair plus 3 external. What would this need? Trigonal pyramidal. In other words, even though those 3 are not on the same plane, okay, it does form a little short stubby pyramid. Okay. What shape do I have here where I have 2 lone pairs? Still, my potential is 4. So I'm still working out of that column that has 4. So I have 2 lone pairs bent, and it actually forms that bent shape. Okay. And we don't have 3 lone pairs for this one. But if we did, we'd call it linear. The next one is a trigonal bipyramidal. The reason why they call it trigonal bipyramidal is because it forms a triangular base pyramid, and you have 2 of them. So trigonal pyramid, trigonal bipyramidal. Okay. Now, when we look at this, what's my potential for the trigonal pyramidal? 5. Okay, so I've got 5 external atoms. If I have 1 lone pair, what's the name? Seesaw. It's like a seesaw. Okay, so if you go to the playground, you get to play on a seesaw. Okay. If I have 2 lone pairs of electrons, what's the name? T-shaped planar. So it forms a T that lies on a plane. Okay, so T-shaped planar. If I have 3 electrons removed, or I'm sorry, if I have 3 atoms removed, what shape do I have? Linear. Forms a straight line. So again, the lone pairs, okay, we don't ever look at lone pairs when we're determining the name. So it forms a line. Okay. Pretty cool. And then the last shape is what? Octahedral. Now why do they call it octahedral? What does it have 8 of? Sides. Very good. So it doesn't have 8 atoms, but if you were to connect the dots and you'd actually have a square-based pyramid, which has 4 sides each. So 4 plus 4 is 8. That's where you get the octahedral name from. Okay, so octahedral is pretty neat. If I take 1 electron away, what shape do I now have? A square-based pyramid. Okay. So it's got a nice little square base and a nice little pyramid. If I take 2 away, what do I have? Square planar. So I have a square that lies on a plane. Okay. And I think that's all we take away from this. And then you could go T-shaped planar, and you can even go linear on this, but we don't do that for this class. Okay. All right. So let's take a look at the examples now that you know the shapes. You've got your octahedral, trigonal bipyramidal, tetrahedral, and all that good stuff. All right, so the first example. And what we learned yesterday about formal charges, we want to continue with that. So we don't want to forget anything on that. Formal charges are a good indicator to help us draw the correct Lewis structure. The instructions on here say first draw the Lewis structure. In other words, use the instructions that we've been using to get to that point. Then name the shape. Actually, we're just going to name the molecular shape, even though it asks for the name with the lone pairs. And then, of course, make sure the formal charges work out. So this is a pretty easy little project. Does it ask if it's going to be a polar compound or non-polar? It doesn't, but let's go ahead and do it anyway, just to give you more practice. So the first thing that we have there, ASO3 with a negative, is that 1? Okay. So what's the first thing that we need to do? Find out how many valence electrons we have. So arsenic brings how many? 5 in group 5A. Each oxygen is 6, and we have 3 of those. Plus the negative 1 means that we are adding 1. So that is 24. Who goes in the middle? Arsenic. And then we have 3 oxygens. Okay, again, let's work smart here based on what we learned about formal charges. What is my overall charge? Negative 1. So one of these oxygens needs to be single bonded. Has a single bond. So I don't care which one you pick. Okay. But for formal charge wise, we need one of the oxygens to be single bonded. Alright, so now that we have 24 electrons, one of those electrons came from somewhere. We don't care where. I had somebody argue with me yesterday saying, you should have to indicate which electron didn't come with them. Who cares? We're sharing. Alright? The metal was gracious enough to give this compound, actually this polyatomic, another electron so everybody could have it. That's what giving's all about. And the anonymous donation is the most precious. All right, so formal charges, we know that the oxygen 0, 0, and negative 1. Let's do a real quick formal charge calculation for arsenic. We can do this in our head. Okay, we first do the assign. How many lone electrons on arsenic? 0. Plus 1 half shared. How many are shared? 10. So half of 10 is 5. How many valence electrons did arsenic bring? 5. So 5 minus 5 is?
0.
We're golden here. That's a beautiful structure. All right, so now that we have the correct Lewis structure, what shape does this form? VSEPR shape. And before you answer, don't worry about how many bonded pairs or shared pairs there are. We don't care about that. All we care about is how many external atoms. There's 3 external. How many lone pairs on the central atom? 0. So 3 plus 0 is 3. So we're going to work out a column 3. And since there's no lone pairs, this is a trigonal pyramidal shape. Okay, trigonal planar. Wow. Trigonal planar. Yeah, planar. ClO2, negative 1. All right, so let's find out how many electrons. Chlorine brings 7. Each oxygen brings, there's 2 of those, and the negative 1 means we have 1 more. So what is that? 20?
Yeah.
Okay. Who's my central? Chlorine, good. And the oxygens go there and there. All right, again, let's work smart here. So we have to have one of these oxygens with what kind of bond? Single. I'm telling you, this is how you do Lewis structures. Okay, so how many electrons do we have shown so far? 16. So we still need to add 4 more. Whatever's left, dump them on the central atom. Okay, there's your 20. Since we had to add 1, put her in there. Okay. Real quick, let's do our formal charge calculation. How many lone electrons on chlorine? 4. How many are shared? So half of that is 3, so 7. How many valence electrons? 7 minus 7, so we're rolling. And the oxygen has a -1. Okay, so what shape does this form? Non-linear. Okay, let's go back. What's the potential for this? 4. So if we had another oxygen here and here, what would the name of that be? If we had oxygen here and here on top and bottom as well, it'd be tetrahedral. So we're working out of that column. However, this forms a bent shape. Okay. Don't let the 2 dimensions psych you out. Yeah, it's 180. No. No, all you need to write now is the shape that the atoms form.
Oh, so I don't have to draw anything?
No, you have to draw. So this forms a bent shape. Is this polar or non-polar? Polar or non-polar? No. I'm sticking to my guns. What did we say? If you have lone pairs, it is polar. Use your imagination. Pretend that this is a double bond. It's bent. Okay, so there's a double bond here and a single bond there. So the lone pairs don't push or pull. What we're thinking is, we're looking at it like that when it's really like that. Okay, so we gotta stop thinking about the 2 dimensions and bring it into the 3rd. It's all right. And there's only 2 exceptions, and I hope I have one of them. If not, I'll give it to you. What is that? IBR3? Okay. How many electrons does iodine bring? 7. Each bromine brings 7. There's 3. Is there a charge on this thing? No. All right. So what is that? 28? So everybody's got to have a formal charge of 0. Good. All right, who goes in the middle? Iodine? And then put the bromines, and I don't care where you stick them. What kind of bonds does bromine want to have? Single bond, so work smart here. Give them their 8. How many electrons do I have shown so far? 24. I have to have 28. Now, what I don't want you to do, because it's confusing, we need to add 4 more. Don't put them in the same quadrant. This is what I do. Give it arms or give it legs, whatever you want to call it. And it helps with the shape, which is pretty cool. So we need to add 4 more electrons, but I don't want to put them in the same quadrant, so to speak. Because on the marker board, you could probably see the difference. On the piece of paper, 4 dots together is a really confusing thing. So when we look at this, okay, this is what our shape looks like. What's the potential for this molecule? 5. In other words, I have 3 external atoms plus 2 lone pairs, so my potential is 5. What shape does this form? Just the atoms alone. T-shaped planar. Very good. So if we had, say, 2 more bromines, we'd have a trigonal bipyramidal shape. However, since we have 2 lone pairs, we have a T-shaped planar. All right, let's double check and make sure our formal charges are correct. How many lone pairs, or I'm sorry, how many lone electrons on iodine? 4 plus 1 half shared, 3. So it's good. Okay. So much easier. You Rn O4 -2. Okay. How many electrons, valence electrons, does radon have? 8. It has all 8. So why in the world would it need to form a compound? It's big. That's why. Oxygen brings 6, and there's 4 of those. The -2 means add 2 more. So what is that? 34? Okay. Who's my central? Radon. And the oxygen, since we have 4 of those, put them around the horn. And again, let's work smart. 2 of these oxygens need to be what? Double bonded, and the other 2 need to be good. And I don't care where you put the doubles, I don't care where you put the singles.
How do you know that? Because it's +2 or -2?
It's -2.
Is that how you know that?
That's how you know, right. So when oxygen has a double bond, it has a formal charge of 0. When oxygen has a single bond, it has a formal charge of -1. So we have to make sure that all the formal charges add up. How many electrons do I have shown so far? 32, right? Okay. So whatever's left, add it to the central atom. Okay. All right, so let's do formal charge calculation. We already know what oxygen's -1 and 0. So how many lone electrons on radon? 2. How many are shared?
All of them but 2.
12?
No.
Stick with 12. So half of 12 is, so that gives us a grand total of 8. How many valence electrons did radon have? 8. So our formal charges are great. All right, now let's make sure that we do this right. What shape does this form?
Seesaw.
Seesaw. Okay. So you've got your top and bottom, and then your 2 sides, and then 1 off to the side. So your seesaw. It's a good time. Go to the playground. All right. Polar or non-polar?
Polar.
Very good. Because we have that 1 lone pair of electrons. All right, SiO2, silicon dioxide. Silicon, how many does it bring? 4. And oxygen, and we have 2 of those. No charge on this one, right? So what is that? 16? Okay. All right, who goes in the middle? Silicon, and then the oxygen. So again, total charge on this compound is 0, so everybody needs a formal charge of 0, so oxygen should have double bonds. Uh-oh. Is this okay?
Yep.
Silicon has 8? Yes, it's very good. So doing the formal charge calculation for silicon, how many lone electrons on silicon? 0, plus 1/2 shared is 4. How many valence electrons does silicon have? Good. Polar or non-polar? Non-polar. Very good. All right. Let me give you the 2 examples, or 2 possible examples. Okay. Oh wait. Let's make sure it's not on your homework. Nope. I don't want to. Okay, it's not on there. Okay. Here's another example. It's blank on the back side, so go ahead and do that. All right. Let's see here. So iodine brings how many? 7, and we have 3 of those. And then we add 1 more electron, right? So how many is that? 22. Okay. We have 3 iodines. Who's the central atom? Iodine. Duh. Now, again, follow the rules. Make sure that you satisfy the external atoms first. And remember, external atoms cannot have more than 8 electrons. Ever. Okay, central can, external never. So what kind of bond does iodine want to have? Single. So give it a single. How many electrons do I have shown so far? How many more do I need to add? 6. So I can put 2 there and give it legs. Okay. Don't crunch 4 in the same quadrant, please don't. Okay. Now, this does not follow formal charges. Why? Why does this not follow formal charges? I'm just going to tell you right now. Iodine can never be double bonded. Okay, so we're not going to swing a pair in between. So again, formal charges is a good rule, but the reason why I'm showing this is to show you the exception of polar and non-polar. So even though formal charges won't work on this, I'm going to stop with the formal charges. How is this a non-polar compound? We've got 3 lone pairs of electrons here. What shape does this form? Linear? Very good. So when we look at it, they all are in the same plane. All 3 of these are iodines, 3 lone pairs. Okay. We always remove from the central axis whenever you're looking at the trigonal bipyramidal shape. Okay. So it is a linear shape. Even though we have lone pairs of electrons, this is a non-polar compound. This is your 1 of 2 exceptions.
So basically, anytime it's linear in this one, it's going to be non-polar.
As long as these 2 atoms are, what? The same. Very good. If they're different external atoms, that throws everything out the window. You're up to see tonight. If you have, and I can't remember what, I can't think of a compound right off hand here, but we'll go X and O's here. Okay, they're not oxygens, and there's no element X. But if you have, say, this scenario, and for whatever reason I'm drawing a blank, I can't remember a compound that does this. Okay, what shape does this form, molecularly speaking, just the atoms alone? Okay, there's, our potential is what? Let's ask that first. Square planar, because we have a potential of 6. So square planar shape is your other exception. Okay, and again, you have that square plane, and the 2 electrons, 2 pairs of electrons don't push or pull. Now, it is very, very rare that they're going to give you different external atoms, but if they did, we're still going to say that it's polar. Now, some people might say, well, what if they gave you, let me give you this. Let's say they did this to you. Ho, ho, ho. Is that polar or non-polar? Different external atoms. And who's to say that they align like that? They could be like this. Okay, so stick with your guns. Different external atoms means you're going to have a polar compound. All right, so for the homework today, do what we did for the examples. Just give me the molecular name, in other words, the shape that the atoms will form. Also, draw the Lewis structure, the correct Lewis structure, as long as formal charges will obey that. Okay.